Now, if you remember, we said that we defined even and odd signals. Okay, so this is a topic of even and odd signals. Okay, we defined an even signal as one which satisfies the property x1 of n is equal to x1 of minus n. So, you change the argument. So, x of 2 same as x of minus 2, x of 3 same as x of minus 3. This is the condition for an even function. On the other hand, if x1 of n is equal to minus x1 of minus n, then this is the condition of an odd function. Okay. Now, we are given the following. We are given that x1 of n is an odd signal, Okay, then you can see what property it will satisfy. We are given that x2 of n is an even signal, Now, given these two conditions, okay, I am going to create a product signal x1 of n equal to x1 of x of n is equal to x1 of n times x2 of n. Now, the question is, does x of n have either of those two properties? Remember, x1 was odd, x2 was even. Now, the best way to do it is to substitute for n with minus n. Okay, look at x of minus n. What is this equal to? This is equal to x1 of minus n times x2 of minus n. Okay, x1 of minus n is a odd signal. So, x1 of minus n is the same as minus x1 of n. Okay, go back and look at the properties of an odd signal. This is equal, and x2 of minus n is an even signal. So, therefore, that will be equal to x2 of n. So then you get this following result, that x of minus n, this product of these two sequences comes out to be minus x1 of n times x2 of n, that is the same as minus of x of n. Okay, if this condition is satisfied, is it an even signal or an odd signal? This means it is an odd signal. That means x of n is odd. So, I took a product of two sequences, one of them was even, one of them was odd, then I multiply them, the result is odd. Okay, this actually is a very interesting, very simple property, but it is present. Now, if x1 of n had been even and x2 of n also had been even, and you multiplied them together, x1 of n, x2 of n, the resultant will still be even, right. If you substitute minus n, both of them will produce the same function. So, therefore, it will be even. But what is more interesting is the last one. If x1 of n is odd and x2 of n is also odd, the product x1 of n, x2 of n, you substitute minus n, both of them will produce a minus sign and minus sign will cancel, and what you will see is that this product of two odd sequences is actually even. Okay. So, again, this is something that is a simple extension of the basic observation. It's good for you to be able to work with this. Now, there are some further interesting properties which I would like you to also be aware of. Supposing we are given if x of n is odd, okay, we are given this condition. Okay, then what we say is x of n must be equal to minus x of minus n. That is the property, minus of x of minus n. Now, substitute n equal to 0, what do you get? X of 0 is equal to minus x of 0. Okay, bring x of 0 to this side, 2 times x of 0 equal to 0, which means for an odd signal x of 0 must always be 0. Okay, why? Because x of 1 same as x of negative of x of minus 1, but x of 0 has to be negative of itself. So which means that it has to be always 0. So the first thing, if somebody were to tell you, give you a sequence and say check is this sequence odd, first thing is you do is you don't start checking everything, just say is x of 0 0. If it's not 0, then it is not. Okay. The second one, supposing somebody were to ask you to sum over infinity all the samples of an odd sequence, minus infinity to infinity. Okay, it's a huge numbers are coming. You don't know whether it's correct. So what you do is look at this particular property. You can break up this sum from minus infinity to minus 1 x of n plus x of 0 plus n equal to 1 through infinity x of n. Okay, this one summation, I split it as minus infinity to minus 1 as one summation x of 0, and now because it is an odd function, this has to be equal to 0. So I can drop that out from here. Okay, now look at the terms in the second summation. This is x of 1 plus x of 2, x of 3 dot 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 all the way to infinity. Now look at the summation here, x of minus 1, x of minus 2, x of minus 3 and so on all the way to, so this is the two summations. These two will cancel each other because the one is the negative of the other, right, and you are adding them together. The x of minus 2 will cancel x of 2. Similarly, x of 3 will, minus 3 will cancel x of 3. So when you do the summation, this summation for an odd signal must be equal to 0. An odd signal will add up to 0 always. This is a very useful result to have. Two very nice properties of odd signals. You just want to keep that in mind. Okay, I give you a minute to think about it. What we have said is product of two odd signals is even, product of two even signals is even. If one of them is odd, one of them is even, the product will come out to be odd. So basically that's the result. And of course, if you look at an odd sequence, x of 0 must be 0 and you will have negative values on either side. So if I am summing from minus infinity to infinity, the sum will end up being equal to 0. Now there are some very interesting simple calculations that you can do. Supposing I told you that, okay, this is another example. X of n is equal to the unit step. Okay, I would like you to sketch the even part of x of n. Okay, how do you get the even part? You say 1/2 of x of n plus x of minus n, u of minus n. Okay, so sketch it. This is u of n. Okay, this is u of n. U of n. U of minus n is the flipped version. U of minus n, mirror image of that starting with n equal to 0. So this is all 0 valued samples. When you add these together, what you get, the even part comes out to be something that looks like this. This has a height of 1. On the right side, you have all samples which have equal to half, height of half. And on the left side also, very interestingly, all the other samples except n equal to 0 have got the height equal to half. Okay, you can verify that's what, so this has a height equal to 1. Now sketch x odd of n, 1/2 of u of n minus u of minus n. Okay, these two you have to subtract. Then you get a very interesting sketch. So by the way, this is x even of n. I'm going to sketch x odd of n. X odd of n, the sample at n equal to 0 cancels out. Then everything to the right has got a value equal to half, equal to value half. Everything to the left negative n has got a value minus half. Okay. Add these two together, what will happen? All the minus halves will cancel. Okay. 1 and 0 will become 1 at n equal to 0. Then all the halves will add together to produce 1 for all positive values. So, you can verify that x even of n plus x odd of n will be equal to x of n, which has to be equal to, in this case, u of n. And you can easily verify that this is indeed the case. Okay. And of course, u of n is an infinitely long sequence. We can also look at some simpler sequences. I would like you to be able to do that as well. Supposing x of n is given as a finite length sequence, 4 comma minus 2 comma 4 comma minus 6. Okay. Important thing to note, need to know where the origin is. Okay. So, basically you can add zeros on either side. This is where the, so obtain the x even of n. Okay. Take the original sequence, flip it around, and then take half. This comes out to be 2 comma minus 4 comma 4 comma minus 4 comma 2. Okay. Important thing to note, this is the origin, this is the origin. X of 1 and x of minus 1 are the same, x of 2 and x of minus 2 are the same. So, that's a property of an even sequence. Okay. And look at x odd of n, go through and do the calculation. This comes out to be 2 comma 2 comma 0 minus 2 comma minus 2. Okay. This is the origin, has to be equal to 0 for an odd function. And look at minus 1 and plus 1, they are negatives of each other. Minus 2 and plus 2 are negatives of each other. So, again you can verify that this is indeed the case. And as a final calculation or an example, I would like you to do the following, which is to look at a complex sequence. So, this is a example which is a complex sequence. So, x of n has got complex valued samples. The first sample is 0, second sample is 1 plus j4, j is square root of minus 1. So, basically 1 plus j4 is a complex number, minus 2 plus j3, 2 minus j4, minus 6 minus j5, and 7 and minus j3. Okay. There is a 0, there is a 7, that is also a real number. Then there is one which is purely complex, that is minus j3, and all of the others are have got real part and imaginary part. Okay. Please verify, again you know the definition of a conjugate symmetric sequence. X of n, 1/2 of x of n plus 1/2 of x of n plus x conjugate of minus n. Okay. So, we need to know which the origin is. 2 minus j4 is the origin, and please go ahead and look at the conjugate symmetric portions. Okay. This sequence will be equal to, please verify, j 1.5, 4 plus j2 minus 4 plus j4, 2 minus 4 plus j4, 4 minus j2 minus j 1.5. Okay, this is the origin. Plus 1 and minus 1 are complex conjugates of each other. okay, plus J4, something is wrong here, minus 4, minus J4, sorry. Okay, yeah, it has to be complex conjugate, so therefore this is minus J4, they are complex conjugates of each other. Okay, minus 2 is a complex conjugate of x of 2, minus J2 plus J2, minus J1.5 and plus J1.5, the complex conjugate. So basically the conjugate symmetry is observed in the conjugate symmetric sequence. Conjugate antisymmetric sequence, CA of n, again you can do the simple calculation, it will be x of n minus x conjugate of minus n. Please verify the following: minus J 1.5 minus 3 plus J2, 2 minus J minus J4 minus 2 minus J 3 plus J2 minus J 1.5. Okay. So basically if you take the conjugate of the sequence of the particular index, it will be equal to the negative on the other side. So basically you can see that this is the origin, okay, and these two will be negative of each other. Similarly, these two will be negative, these two will be negative. Okay. So please verify that we have satisfied the conditions for conjugate symmetry and conjugate antisymmetry, and then if you add these two together, you should get back the sequence that is on top. So verify that also, that x of n is equal to x conjugate symmetric of n plus the conjugate antisymmetric sequence of n. Okay. Those are two very, very useful properties for you to work with. All right, so we have done, looks like we have done a lot of examples. I hope this will reinforce the concepts that you have studied, and definitely the idea of this course is that you should have the basic concepts and very thorough of the concept, of the definitions. If you are anytime in doubt, go back and look at the definitions, look at a few examples, and then things will become very, very clear. All right, so now we move on to looking at some of the other concepts that we had covered in the last lecture. So let us start with the property of linearity. We said that a discrete time system is linear if it satisfies two properties. One is scaling. If I scale the input by a factor A, will the output get scaled? This is called the property of homogeneity, or also called the property of scaling. The property of additivity says if x1 produces y1, x2 produces y2, if I add these two together, do I get the output y1 plus y2? Now combining scaling and additivity, we say that a discrete time system is linear if it satisfies the following property. Okay, x1 of n producing y1 of n by means of the linear time of a system T. Okay, this is a transformation. Similarly, x2 of n, same transformation, produces y2 of n. So this is the given. This is what is given. Okay, now if I take a times x1 of n plus b times y of n, x2 of n, and add them together and pass it through the same system T, do I get a times y of n, y1 of n, that is the scaling property, and b times y2 of n, scaling? Additivity, the input was added, did the output also get added? Do you satisfy these conditions or not? Okay, very, very important. Okay, always good to verify this by means of simple examples. Okay, the first thing, example, I will give you a system and you tell me if it is linear or not. Y of n is equal to 2 times x of n. It is an amplifier. Okay, it takes your input signal, scales it by a factor of 2. Okay, supposing we have x1 of n and it produces y1 of n. y1 of n will be equal to 2 times x1 of n. That's the property. If I have x2 of n, y2 of n will be equal to 2 times x2 of n. Okay, and easy to verify that if I feed in alpha times x1 of n, what does the system do? It takes whatever is the input, multiplies by a factor of 2. So, y of n will be equal to 2 times alpha times x1 of n, that is the same as 2 times y1 of n. Okay, so scaling property is satisfied. So, we can put down saying, okay, scaling or homogeneity tick mark. Addition. If I do x1 of n plus x2 of n, what will my system do? It will take my input and then multiply it by a factor of 2. So, x1 of n plus x2 of n, that is what it will do. Okay. Expand this, 2 times x1 of n plus 2 times x2 of n, which is the same as y1 of n plus y2 of n. And you can also do scaling and other things. Okay. So, what I would like you to verify is, using this as a basis, you can verify that alpha times x1 of n, alpha or a does not matter, some scale factor, plus beta times x2 of n, does it, when you pass it through this transformation, does it produce for us alpha times y1 of n plus beta times y2 of n? The answer is yes, and therefore, this system is linear. Okay, this system, based on these tests, we will declare this to be a linear system.
So that should be alpha, right?
Which one?
2y1 of n you have written, scaling.
2y1.
Alpha x1 of n will produce.
Alpha x1 of n will produce alpha y1 of n.
Only alpha 1. No, you have written 2y1 of n. Scaling.
Oh, correct. No. It will be 2 alpha x1 of n plus 2 beta x2 of n.
Sir, that red line. After the x1 of n produces 2x1 of n.
Yes.
x2 of n produces 2x2 of n.
Correct.
Below that you have written alpha.
If I supply alpha x1 of n, what I should get would be 2 times the input. So, it will be 2 times alpha times x1 of n.
That should be alpha y1 of n.
Ah, correct. That is correct. Thank you. Yeah, this should be equal to alpha. That is our scaling. Yeah, input is scaled by alpha, output is scaled by alpha. Absolutely correct. Okay. All right. So, one very interesting observation we know from trigonometry and from algebra, that y of n equal to 2 times x of n, that is a straight line, right? Y of n is equal to 2 times x of n is a straight line equation. So, analytical geometry, a straight line. Okay, what is the slope? Slope is equal to 2, slope equal to plus 2, and the line passing through the origin. Passing through the origin. Okay. Now, this actually gives a very important input, observation. So, if input is 0, that means you have not applied any input, there is nothing, right, 0. Then the output must be 0. Output must be 0. Okay. Why is that? Scaling. If I put alpha equal to scaling as 0, output has to be 0. It cannot be something else, right? Now, look at the equation of another straight line that we are all very familiar with. Okay, y of n is equal to 2 times x of n minus 3. is this linear? Okay. Intuitively you may say, well, y is equal to 2x is linear, y is equal to 2x minus 3 must be linear, but let us check. Okay. So, if I have x1 of n, what does it produce for me? y1 of n is equal to 2 times x1 of n minus 3. x2 of n produces for me y2 of n equal to 2x2 of n minus 3. Okay. Now, if I take alpha times x1 of n, what will I get? Y of n will become equal to 2 times the input time minus 3. So, it becomes 2 times alpha x1 of n minus 3. Okay. So, now on the other hand, what I am looking to get is alpha times y1 of n. Alpha times y1 of n comes out to be 2 alpha x1 of n minus 3 alpha. Okay. Notice that the first term is okay between these two and these two. Okay. Or sorry, not that one, here, between this and this, but the second term not okay. These two are not the same. So, scaling the input does not scale the output. So, this basically says scaling not satisfied, not satisfied. Okay. You can start right, so you can stop right there. If unless both of them are satisfied, only then linearity. So, this is not satisfied means not linear. Okay. You can also verify the following. Supposing you gave the input x1 of n plus x2 of n, what will this system produce for you? It will produce y of n equal to 2 times the input, 2 times x1 of n plus x2 of n minus 3, right, 2 times the input minus 3. So, this is the same as 2 times x1 of n plus 2 times x2 of n minus 3. On the other hand, if you had taken the output, right, y1 of n plus y2 of n, if you looked at each of those individual outputs, this would have been equal to, gives, this would have been equal to 2 times x1 of n minus 3, that would have been y1 of n, plus 2 times x2 of n minus 3. So, the sum of these two would have been 2 times x1 of n plus 2 times x2 of n minus 6. Okay. This is satisfied, this is satisfied, this is okay, this is okay, this is not okay, not okay. So, basically additivity also fails. Additivity is also violated, not satisfied, not satisfied. Okay. So, this also leads to the same conclusion that it is not linear. Okay. Now, could we have guessed that this would have been, this is the case? You could have, if you set x of n equal to 0. Okay. So, if x of n is equal to 0, what happens to y of n? Y of n comes out to be minus 3, non-zero. So, therefore, there is a violation of the condition of linearity, but the correct way is you check for scaling, check for additivity. If one of them is not satisfied, you declare saying that this condition is not satisfied, and therefore, this system is not a linear system. Okay. 0 input, 0 output, also a property of LTI systems, linear systems. So, you can also verify that property is also satisfied.